Hello everyone. This is part 1 of a video series providing an exposition of the paper by Duque et al. 2020, Timing Social Distancing to Avert Unmanageable COVID-19 Hospital Surges. The purpose of this video is to explain the technical content of this paper, making it more accessible to a wider audience. This paper draws on knowledge of different disciplines, such as SEIR epidemiological models, mathematical optimization, and queuing theory. This article, written during the COVID-19 pandemic, presents a mathematical modeling strategy to assist policymakers to make short-term shelter-in-place decisions in such a way as to minimize the number of days spent in lockdown while ensuring that hospital capacity is not overloaded due to COVID-19 hospitalizations. To create a mathematical model representing a COVID epidemic in a particular area, everyone in the population is grouped into one type of disease compartment: susceptible, exposed, infectious, or recovered. The susceptibles have never had the disease before. The exposed people have been infected with COVID-19 but are not able to transmit the disease yet due to a latent period. There is a slight complication though, in that in Duque et al. From the supplementary information on page 4, the mathematical model accounts for some disease transmission from the exposed group, as the red box shows. The infectious group are infected with COVID-19 and are able to transmit the disease. The recovered group have immunity, and it is assumed that they cannot become reinfected. We can see that individuals flow from the susceptible compartment to the exposed, to the infectious, and then to either the recovered or deceased compartments. Differential equations can be constructed that describe the rate of change with respect to time of the numbers of individuals in each compartment. Because individuals in the infectious compartment can transmit the disease to individuals in the susceptible compartment, the time rate of change of the susceptible compartment is directly proportional to the number in the susceptible multiplied by the number in the infectious compartment. And we use a proportionality constant, in this case beta. Using similar logic, the time rate of change for the other compartments can be expressed mathematically. Since everyone in the population belongs to one compartment at any one time, the total population is assumed to be constant, so we neglect the number being born and the number of deaths not due to COVID. This means that the time rate of change in the S, E, I, R, and D compartments all sum to 0, and this helps us to construct the differential equations for each compartment correctly. In Duque et al., the infectious compartment is subdivided into infectious with symptoms and infectious without symptoms. Duque et al. Also accounts for different infectiousness of the symptomatic and asymptomatic groups, shown by the coefficients omega A and omega E. Now that we have covered the basic SEIR model, let's introduce a new concept: the contact matrix. Each entry of the contact matrix represents the average number of individuals of group J that contacts with one of group I over a 24-hour period. Contact matrices are constructed from survey data, where individuals of a particular age and risk group are asked to record the individuals they come into contact with over a defined period, in this case 24 hours. Contacted individuals are recorded only once, and a contact is defined as skin-to-skin or a conversation with 3 or more words. For more information, see the paper by Mosong et al. If we want to know the rate at which group I are getting infected, then we perform the following calculation, where Si is the number of susceptibles in group I, beta is the transmission risk or rate per contact, Cij represents the number of individuals of J that contact with one of group I, and Ij over Nj represents the proportion of group J that are infectious. The sigma sign indicates that we are summing over all groups J. The groups I and J in Duque et al. Are further categorized into a particular age and risk group, A and R respectively. So instead of summing over J, we sum over all the risk groups for a particular age, and then we sum over the age. Duque et al. States that the basic reproduction number is derived from the fixed and fit parameters listed in tables S7 and S8 using a next generation approach. We will now provide an explanation for what this means, and this explanation is incomplete because I don't fully understand the concept yet. A fuller explanation may be provided in a subsequent video. Consider an SEIR model with infectivity in the exposed group. The equations for the time rate of change in each group is given by the following equations. Our aim for this next few minutes is to write the next generation matrix for this model. Step 1 is to identify the infected states. In this case, these are the exposed group and the infectious group. Step 2 is difficult for me to explain, but it involves assuming an infection-free steady state and performing scaling. We set the number of exposed, infectious, and recovered to 0. So the total number in the population equals S. This is because S plus E plus I plus R equals to N, which is the total number. And if E, I, and R are 0, this means that S equals to N. Scaling means that for the infected states E and I, we divide S by N. So we replace the S in these equations with 1. The time rate of change for the exposed and infectious become linear equations. So for the rate of change in the exposed group, the equation becomes linearized to beta I, beta var epsilon E minus VE. And this is a linear expression. Similarly, the time rate of change for the infectious group is also a linear expression. We now order the terms in the equations. There are 2 infected states, E and I. People travel from the exposed group to the infectious group, so the exposed group comes first. The order that we want is terms containing beta and E multiplied together, then terms containing beta and I multiplied together, then other terms containing E without the beta, and finally the other terms containing I without the beta. The left part of this informal matrix will give rise to the transmission matrix T. The right part of the informal matrix will give rise to transition rise to the transitions matrix. Next, we perform partial differentiation, respecting the order of variables. The transmissions matrix T represents the epidemiological events that lead to new infections. Looking at this matrix more closely, the entry in beta top right represents the rate at which individuals in the I infected state give rise to the E infected state. The entry beta var epsilon represents the rate at which individuals in the E infected state give rise to the E infected state. We've obtained the transmissions matrix and the transitions matrix. The next step is to find the next generation matrix. This is done by calculating negative t times sigma to the minus 1. We perform this calculation by hand, or we can also use Python programming to do this, particularly for larger matrices. The basic reproduction number is then the dominant eigenvalue of the next generation matrix. We will now shift to a different topic, the Halfin-Whitt approximation. The Halfin-Whitt approximation approximates the probability that an arriving patient needs to wait for service. The hospital can be described by a MMS queuing system. According to the model, the arrivals are random probabilistic events modeled by a Poisson process. The service time for a particular patient is also probabilistic, following an exponential distribution. The S in MMS stands for the total number of servers in the system. In this case, the total number of hospital beds available for COVID patients. According to the Halfin-Whitt approximation, for a high utilization ratio approaching 1 from below, and if the total number of servers in the system is more than about 80, the probability that an arriving patient has to wait is given by the equation shown. The bold phi represents the cumulative normal distribution. The phi in the denominator represents the normal probability density function. K is calculated by the equation shown, with S representing the total number of servers in the system, lambda representing the arrival rate, and mu representing the service completion rate. The Halfin-Whitt approximation is difficult for me to derive, but let's start by talking about the MM1 queue with one server. Suppose the service completion rate is greater than the arrival rate of patients. We may still have a queue of customers waiting because arrivals and service completion are random variables. We can safely assume that the queue would not keep growing longer. After an infinite amount of time has passed, we say that the total number in the system, designated by q as a function of time which is infinite, is in steady state. This symbol q is found in the Halfin-Whitt paper referenced by Duque et al. When we talk about the MM1 and MMSQ, we need to derive the Chapman-Kolmogorov equations. Also, the lambda representing arrivals and mu representing service completion are memoryless events. They do not depend on the number of customers in the queuing system. An important step in deriving the Chapman-Kolmogorov equations is to replace lambda with lambda delta t in the probability mass function formula for the Poisson distribution, and likewise replacing mu with mu delta t. We then performed a Taylor series expansion of the Euler number term and removed delta t squared and higher order delta t terms. This is because the delta t represents a small period of time. We then obtain the probability of 0, 1, and more than 1 arrivals, approximated with, with these Taylor series expansions. We then find the probability of no customers in the system at time t plus delta t. This is found by p0t multiplied by no arrivals in delta t plus the probability of having one customer in the system at time t multiplied by the probability of one service completion in delta t. So it is the products of probabilities added together. In a similar way, we find an expression for pi t plus delta t, where I is one or more customers in the system. We then find an expression for the following expression. And then we take the limit as delta t goes to 0. This gives the Chapman-Kolmogorov equations for the MM1Q. For certain reasons, we are interested in situations where the probability of being in state I does not depend on time. So I think we can say that the probability that there are I customers in the system is not dependent on time. Then we can show the following. To apply a similar logic to the MMSQ, we need to consider three situations. When the total number in the system is less than the total number of servers, the departure rate is n times mu, where n is the total number in the system. This is because if n is less than the total number of servers, that means that everyone is going to be served by the set of servers. And so the total departure rate is n times mu, where mu is the departure rate for one individual server. When the total number in the system equals the total number of servers, we have n equals to s. And so the overall departure rate from all the servers is n times mu, or s times mu. In the third situation, we have the total number in the system is greater than the total number of servers. In this case, all the servers will be busy serving customers. And so the overall departure rate is s times mu, while n is greater than s. Thank you for listening. This concludes part 1 of the video series.